Hello everyone, I'm Huiyu and I'm a PhD student from Southeast University. Today I'm very happy to share with you our paper called Locally Differentially Private Frequency Estimation based on Convolution framework. So what is LTP frequency estimation? Imagine that there are m users and each user possesses a private value. We assume that all these values are from a specified domain with a domain size of D. And the server is trying to aggregate all these values and figure out the frequency of each value among all users. To protect their own privacy, the users will use some privacy-preserving techniques to encode and perturb their own private value locally and upload the results to the server. And the data collector will aggregate the report from all users and output the estimation of the frequencies. Since each user has added noise to the private value, the total added noise of LDP is significantly high, but without relying on a trusted data collector compared to centralized DP. And why would we need to implement the private frequency estimation? Well, frequency estimation is a fundamental task in the private data analytics and is a key building block of other advanced tasks. For example, it can be used for range queries, it can be used for heavy hitter identification, and it can also be used for item set frequency estimation. It also has many real-world applications. Google collects users' web settings and browsing behaviors to help identify uncounted threads. Apple collects commonly used emojis and phrases to enhance quick type suggestions. And Microsoft collects the telemetry data in Windows to identify possible issues with applications and improve user experience. We use the standard local differential privacy definition to define the privacy. Generally speaking, for any two different inputs V and V prime, the probability of producing the same output Y in an LDP protocol should be very similar. We also use a pure local differential privacy definition from Tianhao Wang, especially the idea of support. It builds a straightforward connection between outputs and inputs. After encoding and perturbation, the output of the LDP protocol may support some certain inputs. In pure LDP, there only exist two probability values, P and Q, where P is a probability that the output supports its original input, and Q is a probability that the output supports a certain input instead of its original input. For those who are not familiar with the definition, assuming a simple yes or no question, and we have a yes as the input. However, after the LDP perturbation, the output may remain the same yes with a high probability, or may become a no with a low probability. Obviously, the output yes only supports the input yes, and the output no only supports the input no. Here, one output only supports one input. In more complex cases, one output may support multiple inputs at the same time. And nowadays, many LDP frequency protocols can be seen as pure. For pure LDP, there is a general estimation equation to estimate each value's frequency in the aggregation step. The data collector sums the number of all outputs that support value I, and then use the probability PQ and the total number of users M to normalize the count to estimate the frequency. However, there is a problem of noise amplification in this equation, and then we will discuss it later. With all this background information, we can now finally begin to use our convolution framework. By representing the encoding and perturbation step as a circular convolution process, we give a new perspective on analyzing and optimizing the LDP protocols. Existing denoising deconvolution techniques can be applied immediately to the LDP protocols, and the existing LDP protocols only need to modify the aggregation step. They also give two approaches based on linear deconvolution to obtain much more accurate estimation results. For pure LDP protocols, the encoding and perturbation steps can be represented as a circular convolution process, where J is a length D vector consisting of summation of gathered perturbed outputs. F is the true frequencies of each value. H is a length D transfer vector, and N is a length D vector of added noise. From the definition of pure LDP, we can get the transformation probabilities matrix M, where Mij represents the probability of input value I supports value J after the perturbation. then we can obtain the equivalent transformation of the convolution process based on the property of the circulant square matrix. It is worth noting that as long as the transformation matrix is circular, the derivation is valid even if the LDP particle is not pure. Based on the central limit theorem, we can also find the eddy noise follows a Gaussian distribution with zero mean and no variance. With the convolution framework, we can convert the frequency estimation problem into a deconvolution problem with norm J and H and partly norm N. According to the derivation, we can rewrite the sums and substitute this into the previous estimation equation. Obviously, there is a problem of noise amplification in this equation. Then we can find it does not fully take into account the properties of the noise. So can we estimate the frequencies while suppressing the eddy noise to achieve more accurate results? The answer is yes. In fact, the denoising deconvolution is a very classic problem in signal processing, image enhancement, and etc. The various deconvolution techniques have been proposed. Among all these techniques, we believe that linear deconvolution is the most classic technique and is optimal to solve the signal with a Gaussian noise. Linear deconvolution works in the frequency domain. Therefore, we need to convert the circular convolution from the time domain to the frequency domain using the faster Fourier transform. Then we can calculate the linear filter with H and the generalized power spectral density or the PSD of noise and frequencies. Then we use the linear filter to get the estimation results in the frequency domain and use the IIFT to get the final estimation results. We can find that when the signal to noise ratio goes to infinite, in other words, the noise goes to zero or the signal goes to infinite, the term inside the square brackets equals 1. Then the linear filter is just the inverse of the degraded data and has the same effects as the original estimation equation. However, as the signal to noise ratio falls at specific frequencies, the term inside the square brackets also falls, which means the linear filter automatically adjusts the filtering intensity according to the signal to noise ratio. To implement the linear deconvolution in practice, we need to estimate the PSD of the true frequencies F and the added noise N. We use the expected PSD of noise as the estimation to use in linear filter, and we prove that it can be viewed as a density vector with the sum of variance of all added noise. And there is an exception for protocol that one output only supports one input. In that case, the first value is 0. Since the PSD of F can be obtained by exploring F, and once we get the estimated PSD, we can implement the linear deconvolution to get the final estimation results. We propose DW and IIW approaches based on whether the approaches run iteratively. In DW, we use the result of the original estimation equation to estimate the PSD of F by default. However, if we have more accurate estimate, we can also use that. For example, we can use DW together with other calibrated approaches and use their output as input to the DW. The IIW iterative based on the fixed points to update the estimate. And by default, its first output will be the same with DW. We propose the IIW approach to make the convergence point independent of the initial value. However, we find that some initial values may have better estimates during the convergence process, like the IW-J uses the J as the initial value. Because we find that the linear filter only achieves the optimal performance in smooth dataset, we also propose the AMRP method to enhance the performance on the non-smooth signal in linear deconvolution. The main idea of the AMRP method is to obtain the average performance among multiple random orders of received signal. We conduct the experiments on 3 datasets. Text dataset is quite smooth, and the other 2 are extremely non-smooth. As KRR and OUE achieve the best accuracy in small and large domain size respectively, we chose KRR and OUE as baselines. We also chose the smooth method for the smooth text dataset as a competitor. Here is the mean square error experiments. The first row is KRR, second row is OUE, very epsilon. We can find that our proposed approaches greatly improve the accuracy of existing LDP protocols on the smooth datasets. For non-smooth datasets, our approaches are still effective, although the improvement is limited. Since our proposed approaches are based on Fourier transform and Wiener deconvolution, the limitations are also inherited. Fourier transform cannot reflect features for non-stationary or non-smooth signals and has Gibber's phenomenon for jump discontinuity in signal. And we can say the running artifacts in the functional approximation in Fourier transform. Wiener deconvolution also requires the signal to be weakly stationary to achieve the optimal performance. Therefore, in our future work, we mainly want to enhance the performance of our proposed approaches on non-smooth datasets. Maybe we will replace the Fourier transform to wavelet transform. We will also try other deconvolution techniques in the future. Thanks for listening. I'm willing to answer any questions.
Any questions?
Maybe I have one question.
Yeah, go ahead.
Hi, Huiyu. As you mentioned, maybe if my understanding is correct, in your paper you consider the domain size is finite case, right? I mean the D should be finite number. So is
yes.
that possible to extend your work to infinite case? I mean D is very large or even infinite.
It can be worked in very large. In fact, the larger the D, the more effective our proposed approach. But for infinite, maybe it's not that because it should be a transform to frequency domain, and this there may be some problems here.
Okay, I see. Thank you.
Okay, we still have some time for questions. Okay, maybe I can ask you some questions. One question, I'm not sure whether you have mentioned it. Is your modified estimator unbiased or not?
I believe the estimator should be unbiased because the Wiener deconvolution is an unbiased estimator. I believe that it is unbiased.
Okay, is it you believe it or you have proved it in your paper?
I do not prove it, but I have read some papers. They mention that the Wiener deconvolution should be unbiased.
Okay. Okay. Another question is, do you think your new estimator is more robust than existing estimators? Robust, I mean by like poisoning attacks. Like you have some fake users, fake clients, they send arbitrary data to the server and you estimate, maybe you will estimate some wrong frequencies. You see what I mean?
I know. I think the robust should be the same. If we want to make it more robust, we should add some like check method to determine whether it is a fake user report or not. Maybe we can determine by the abnormal frequency friction in the after the transform by that.
Okay. Okay. Yeah. Thanks for the answers. Okay. Let's thank the speaker again.